Okay, number 6. The function g has derivatives of all orders, and the Maclaurin series for g is right here. And so part A asks, using the ratio test, determine the interval of convergence of the Maclaurin series for g. So the first thing we want to do is, as the question tells us to, is use the ratio test. So now what does this mean? This means we're going to do the n plus 1 term over the nth term, which is the same thing as writing the n plus 1 term times the inverse or the flip of the nth term. So the first thing we want to do is, if we look at this equation, the first thing we see is that there's an alternator, so we can just go ahead and scratch that out. And so now we have this right here, and we want to find the n plus 1 term. So we're going to do x to the 2n plus 1 over 2n plus 1 plus 3, and then multiply this by the reciprocal of the nth term, which is 2n plus 3 over x to the 2n plus 1. And so now the first thing we want to do is just simplify this, and what we can do is this will turn into 2n plus 5 because you distribute the 2, and then the numerator will turn into x to the 2n plus 3. So now that we have this, we have x to the 2n plus 3 over 2n plus 5, and we can't cancel anything here, but we can cancel out stuff here. And so once we do our canceling, we get left with x squared. So then this equals x squared times 2n plus 3 over 2n plus 5. And then, okay, so now we're going to take the limit of this as n approaches infinity of, this is 2n plus 3 over 2n plus 5 times x squared. And so what we can do is we can just L-hop this, and then that just turns into, it's just going to cancel out and turn into 1. And so we get x squared. So then now that we have x squared less than 1, we can compare it to be greater than -1 and less than 1. And this is in order to find the interval of convergence. And so now that we have these two numbers, we can plug them back into our original equation, which is -1 to the n x, but in this case, our x is going to be -1 to the 2n plus 1 power over 2n plus 3. We're going to do the same thing on the right side, but with positive 1 as our x. Oops, we'll erase that. Like this. This is over 2n plus 3. And now, as you'll see, both of these have alternators. So what we want to do is we want to check if they converge or diverge by the alternating series test. And so in order to do that, what we want to do is we just want to plug in some terms, and we'll see that when you plug in 1 for x, 2, 3, 4, and then we'll just try 11, you get 1/5, -1/7, 1/9, -1 over 11, and then this one is 1/25. And then on the right side, we have, do the same thing, same numbers, and 11. You get actually the same number, it's just with flipped signs. So this would be -1/5, +1/7, -1/9, +1/11, and -1 over 25. And because they both converge, that means we're going to use brackets, and the interval of convergence is from -1 to 1.
Alright, part B. The Maclaurin series for g evaluated at x equals 1/2 is an alternating series whose terms decrease in absolute value to 0. The approximation for g of 1/2 using the first two non-zero terms of this series is 17 over 120. Show that the approximation differs from g of 1/2 by less than 1 over 200. So it says that the approximation uses the first two terms, so that's x over 3 minus x cubed over 5, and then when you plug in 1/2, you get the 17 over 120. And it's asking you to show that g of 1/2, the difference between them is less than 1 over 200. So then for g of 1/2, then you include the error, which would include the third term. And so if you find the difference between the first two terms, and with the third term, the difference is just going to be the third term. So then you have the third term x to the fifth over 7, and then you plug in that 1/2 to make that 1/2 to the fifth over 7, and then this equals to 1 over 224, and that is less than 1 over 200. Is that it?
Are you recording still?
Okay, I'm recording it now.
Okay. So, sorry. So basically, we had to find the first three non-zero terms of g of x. So we got g right here, right? So these are the first three terms, right? So all we gotta do is take a derivative of it, right? Derivative of it. So x over 3, right? What does that do? Andrew, answer the question.
It turns into 1 over 3.
Why? Because that's x, so it goes to 1, right? Right. So 1 over 3. Then we got negative x cubed over 5. 5 is constant, right? It's constant. Keep the negative there too, right? So then we got a derivative of this. So x cubed, 3x squared. And then we got positive x5 over 7, because we got x5 over 7, it's positive, and the 7 stays the same, right, constant. So then we got a derivative of it, 5x4. So our first two terms are 1/3 minus 3x squared over 5 plus 5x to the 4 over 7, right? Now it asks for the general term 2. So how are we gonna do that? First things first, I'm a realist. Alternator. Gotta have an alternator in there. So let me draw this real quick. Alternator, right? Then you're like, oh, but Isaiah, how do we get this and this and this? So we gotta logic it. So let's focus on this constant here first. So it increases by 2 every time, right? So we're gonna use one of our little old fancy equations, but it's all 2, so little, wait for it. Two n plus 1, right? But then, like, oh, what about these x's? There's not one here, but there's one here that increases by 2, right? So, we're gonna logic it. If it increases by 2 every time, it's gotta be x to me, right? And then we put it over. And this is similar to the beginning, right? 2n plus 1. Wait! That's a 3. It's a 3. Uno, dos, tres. That ain't a 1. It's a 3. It's a 3. So, we're left with, and I'll write this fancy for y'all, 1 over 3 minus x squared to the 5, over 5, plus 5x4 over 7.
3x squared. 3x squared. 3x squared.
Sorry, I lied. I lied. 3x squared. Mental lapse happens to the best of us, right? And then you gotta go dot. Like, what's the 53rd one? Wait. There's your answer. There's your answer.